Hi everyone, my name is Cheng, a PhD candidate from Delft University of Technology. I'm glad to have this opportunity to introduce our research, and I will give a presentation about the fracture simulation of fully and partially threaded bolts under tensile loading. There are 5 parts in the presentation. After a brief introduction, finite element modeling of the fully and partially threaded bolts will be given, and then the material properties and fracture simulation of the bolts will be introduced. Bolts are widely used in steel structures for realizing fast execution and the demontability of structural elements, and specifically meant to be used for the structural connections in steel. There are 2 examples shown here. The first one is the bolts used in a prevailing beam to column joint. The second one is the bolts used in the connection of one tower. Obviously, the behavior of bolts affects the performance of the bolted connections. From previous study, it was observed that both tensile fracture and thread stripping failure could govern the final failure of an extended end plate connection. And the upper right picture shows the corresponding bending moment and the rotation curve. Thread stripping failure will result in the reduction of the bearing and deformation capacity, which should be prevented during the design. 2 kinds of bolts, namely the partially threaded bolt and the fully threaded bolt, are used in structural engineering. In the following presentation, PT and FT will be used to stand for them. Generally, these 2 kinds of failure modes would occur when bolts are subjected to tensile loading, as shown here, and the objective of this study is to present a numerical investigation of the fracture behavior of fully and partially threaded bolts and provide insights into the fracture mechanism of bolts under tensile loading. In the direct tension test conducted by Grimsmo, 2 groups of FT M16 bolts and 7 groups of M16 PT bolts with different threaded lengths within the grip were tested. And in the simulation, these 3 tests are selected and simulated to analyze the difference in deformation capacity between FT and PT bolts. These 3 tests are denoted as FT118, PT118, and PT130 in the following analysis. The number indicates the length of the bolt between the bolt head and the nut. The measured dimension of the bolt and nut thread are used in the simulation. See the lower picture. This slide shows the configuration of FT118, PT118, and PT130 test. Antiplastic deformation only occurs in the threaded part of PT bolts. The shank length is reduced from 30 mm to 33 mm for the sake of numerical convenience. And the influence of the test setup deformation is included by an additional elastic spring. The tensile stiffness of the elastic spring is estimated based on the comparison between experimental and numerical results for the bolt tensile stiffness. So the left picture shows the details of the model for these 3 tests, and displacement in y direction is applied on the upper end of the elastic spring to model the tensile loading near displacement control, and general contact is used to model the contact properties. The right picture illustrates the mesh of these 3 models. And for the bolt, in FT180 model, the global mesh size is said to be 1 mm, where for the PT bolts, the element size for the unthreaded part is said to be 1.5 mm, where for the threaded part, it is 0.5 mm. The upper left picture shows the engineering stress strain curve of PT and FT bolts before the onset of necking according to the uniaxial coupling tension test. And it is assumed that the stress strain relation for the threaded part of PT bolts is closer to the measured properties of FT bolts, and the pre-necking true stress strain relationship input in the numerical analysis can be obtained according to the conversion between the engineering stress strain and the true stress strain. And for the post-necking behavior, Lin proposed a combined linear and power post-necking true stress strain relation, which could be calibrated using just a weighting factor W. And this expression is used and extended by Young and Veljkovic to describe the post-necking true stress generation for high-strength steel with weighting factor W less than 0. Quantitative numerical analysis of FT118 and PT130 tests are conducted to calibrate the bolt stress generation using abacus. And the lower left figure shows the numerical force displacement curves against the corresponding experimental results for FT118 and PT130 with different weighting factor. And after calibration, the post-necking stress generation for FT and PT bolts are described by the combined linear and power law with weighting factor W equal to minus 0.3 and 0 respectively in the following analysis. As for the fracture simulation, BW fracture criterion is expressed as the function of fracture equivalent plastic string to stress traxiality. It is concluded that for negative stress traxiality, fracture is governed by shear mode, and for larger stress traxiality, volt growth is a dominant failure mode. While at the stress traxiality between these two regions, fracture may develop as a combination of shear and volt growth models. So C1 and C2 are two constants governing the shear fracture and tensile fracture behavior of a material, which can be calibrated based on pure shear test and uniaxial tension test respectively. And after simulation, the shear factor of both shank, it is inferred that the value of C1 is about 0.3, while C2 is taken as 1.4 to model the bolt tensile fracture. And the steel fracture is realized by defining the damage initiation criterion and damage evolution law in abacus. Only the final fracture modes are considered in this study, and the BW fracture criterion can be taken as the damage initiation criterion, and the damage evolution is defined by the displacement tab with a very small displacement at failure, such as 0.01, to achieve the sudden fracture shortly after the damage initiation. The left picture and the lower right picture show the numerical force displacement curves of FT118 and PT130 against the corresponding numerical results. And these two tests have the same tensile fracture failure mode but different tensile deformation capacity. And in the experimental test of PT118, all 5 tests exhibit the thread stripping failure. Obviously, the PT bolt with tensile fracture failure mode have much less ductility compared to the FT bolt. And after calibration using different C1 value, it is concluded that for the shear fracture simulation of the bolt shank, C1 should be about 0.3, but for the thread stripping failure simulation, the value of C1 should be less than 0.1. This is because the threads have much less remaining fracture plastic string, since the thread rolling process would introduce large plastic deformation in the threaded range. And this slide shows the damage index and equivalent plastic string distribution at the load close to the fracture of the simulated test. And the necking phenomena are obvious for FT118 and PT130 with the initial fracture occurring in the core of the bolt rod, as shown here, and almost no damage occurs in the engagement part of bolt and nut sheds. And for PT118, with only 2 4 threads in the grip length, no obvious necking phenomenon can be observed, as the thread stripping failure prevents the development of the necking in the threaded part. As for the plastic strain distribution, the maximum PEQ is about 0.8 for FT118 and PT130 with bolt tensile fracture failure, while the maximum PEQ for PT118 is only about 0.1 occurring in the thread shear regions with final thread stripping failure. It is considered that the shear area of the bolt thread in the upper engagement range is slightly reduced, as the smaller necking would also occur in the upper engagement chains due to the very short threaded length in the grip length of PT118. And this slide shows the tensile fracture failure mode of FT118 and PT130, and the tried stripping failure mode of PT118. The former is simulated using C1 equal to 0.3, and the latter is simulated using C1 equal to 0.1. In fact, the thread shear fracture plastic string has a decreasing trend from the thread rod to the thread crest, since the introduced plastic string has an increasing trend from the thread crest to the thread rod. And it also to be noted that the thread dimension of the bolt and nut could also affect the failure modes of the PT bolts. The shear area in the engagement region of bolt and nut threads would be reduced if the clearance in the threads get larger. So, in conclusion, the post-necking behavior of the analyzed FT and the PT bolts can be described by the combined linear and power stress strain law with weighting factor equal to minus 0.3 and 0 respectively. And the thread stripping failure and the tensile fracture of the bolts under tension is successfully modeled. The BW fracture criteria with C1 equal to 0.1 and C2 equal to 1.4 can be used to predict the thread stripping failure and the tensile fracture of bolts under tension. And the thread shear fracture plastic string is reduced as the thread rolling process introduces larger plastic string in the thread regions. And for PT bolts with thread stripping failure, the shear area of both threads in the upper engagement region is reduced, as small necking occurs in the upper engagement threads due to the very short threaded length within the bolt grip. And so that's all. Thank you.